All right, let's get into it. Today, we're essentially becoming corrosion detectives. Our case, to figure out if a cathodic protection system, the thing that uses a tiny electrical current to stop pipes from rusting, is actually doing its job. Think of this as your field guide for a real-world investigation, how to gather the right clues, how to spot the red herrings, and ultimately, how to crack the case of corrosion.
So every good investigation needs a plan. Ours has 6 steps. First, we'll define the mission and meet our primary tool. Then, we'll gather our first major clue, the fundamental measurement. After that, we'll unmask a hidden saboteur called IR drop, learn the trick to outsmart it, and then see how to back up our findings with some corroborating evidence using coupons. And finally, we'll wrap it up by analyzing the scene of the crime, the soil itself.
Okay, first things first. What is our mission exactly? Well, we're conducting what's called a CP audit, and it all boils down to answering one single critical question. Is this structure really being protected from corrosion? To answer that, every detective needs their go-to tool.
And here it is, the digital multimeter, or DMM for short. This little device is our #1 tool for gathering evidence out in the field. You can see a technician using one on the left. Its core job, as you can see in the diagram, is pretty straightforward. It takes an electrical signal, a voltage, from our structure and turns it into a clear digital number that we can read and record. It's our reliable eyes and ears on the ground.
With our DMM ready to go, it's time to collect our first and, honestly, our most important clue. This is called the structure-to-electrolyte potential. It is hands down the most common measurement you will ever take in the world of cathodic protection.
So what in the world are we actually measuring? In simple terms, it's a voltage. It's the difference in electrical potential between our metal pipe, the structure, and the dirt it's sitting in, the electrolyte. And to get a stable, meaningful reading, we use a portable reference electrode that we stick in the soil. You could think of that electrode as our trusty anchor point. It gives us a consistent baseline to measure against. This single voltage reading is our first big lead in the case.
Now, this diagram is super important because it shows you what's really happening when we take that measurement. It's a simple electrical circuit. Let's walk through it. E true, that's the real potential of the pipe, the thing we're trying to find. To measure it, we connect our voltmeter, which has its own internal resistance, that's RV. Our test leads, the wires, have some resistance, RT. The reference electrode isn't perfect. It has some resistance, RR. But the really big one to watch here is RS, the resistance of the soil between our electrode and the pipe. Why? Because all of these little resistances can, and do, introduce arrows into our reading.
And that brings us to the main villain of our investigation. I'm talking about an invisible error, a hidden saboteur that can make a pipe that's actively corroding look like it's perfectly protected. This culprit has a name, and it's called IR drop.
Just think about it for a second. You're out in the field, you take your measurement. The number on your meter looks great, and you sign off thinking the job is done. But what if that number, your most important piece of evidence, is fundamentally wrong? That's the danger of the IR drop.
This image does a fantastic job of showing the problem. See those lines radiating out from the pipe? That's the protective current flowing through the soil. As it flows, it creates these voltage gradients in the ground. It's almost like a voltage fog surrounding the pipe. Now, when we put our reference electrode down at point A, our meter doesn't just read the pipe's potential. It also picks up the voltage of the soil at that spot. In this specific example, that error adds 100 millivolts to the reading, making the pipe look way more protected than it actually is.
So let's define it properly. The IR drop error comes straight out of Ohm's law. Voltage equals current times resistance, or V equals IR. It's a voltage drop, the V, that's caused by our protective current, the I, as it flows through the resistance of the soil, the R. This error gets baked right into our measurement, and it's a huge problem because it can completely mask the true condition of our structure. Okay, so we've identified our saboteur. Now, how do we beat it? Well, we need a special kind of interrogation technique, one that forces the IR drop to show itself so we can remove it from our evidence. And that technique is called current interruption.
This graph shows you exactly how it works. Let's focus on that top waveform. On the far left, you see that high, steady line. That's the on potential. It's the number you'd normally read, and it's full of that IR drop error. Now, watch what happens at the exact moment we temporarily shut the current off. See that sharp vertical drop? That, right there, is the IR drop disappearing instantly. The point right at the top of that falling curve, just after the drop, is what we call the instant off potential. That's the prize. That's the true error-free reading we've been looking for.
The whole concept really boils down to this one simple but powerful equation.
EM, our measured potential, will only equal E core, the true corrosion potential, if, and this is the important part, if the voltage caused by the IR drop is 0. By interrupting the current, we momentarily force that IR drop to 0, and in that split second, we can capture the true potential. This is the absolute cornerstone of doing accurate CP field.
Any good detective will tell you you never, ever rely on a single piece of evidence to close a case. You need corroborating proof. And in our world, one of the best ways to confirm our findings is by using something called a CP test coupon.
So what exactly is a CP coupon? Well, that's pretty much what it sounds like. It's a small, carefully measured piece of metal that's the exact same type as our pipeline. We bury it in the soil right next to the pipe and wire it up. Because it's so small and we know its exact size, it acts like a perfect little stand-in for the pipeline, giving us a super accurate, localized measurement without those big, messy IR drop errors you can get on the main structure. Now, there are two main ways we use these coupons. First, we can do that same instant off test, just like we did on the pipeline. We interrupt the current and get a really clean, IR-free reading for that one specific spot. The second method is called a polarization measurement. For this, we physically disconnect the coupon from the pipe and basically watch how fast its potential fades away. If that potential drops really slowly, that's a great sign. It means our coupon was well polarized, which is strong evidence our CP system is working great.
You can't solve a case without understanding the environment where it all went down. For us, that means we have to profile the soil. The properties of the soil have a massive influence on whether corrosion happens and how well our protection system can even work.
And the single most critical environmental factor we need to measure is soil resistivity. You can just think of it as how much the soil fights against the flow of electricity. It's a bit of a double-edged sword. Soil with low resistivity is more corrosive because it lets current flow easily, but it also makes it easier for our protective current to get to the pipe. High resistivity soil is less corrosive, but it makes our CP system work a lot harder. It's a vital piece of the puzzle.
And how do we measure it? Well, the industry standard is the Wenner 4-pin method, which you see here. It's actually brilliantly simple. You drive 4 metal pins into the ground, all equally spaced apart. You use the outer 2 pins to inject a small, known electrical current into the ground. And you use the inner 2 pins to measure the resulting voltage. That gives you a resistance value for that specific chunk of soil.
And this is how we turn that simple resistance reading into our final answer. The formula is rho equals 2 times pi times A times R. Let's break that down. Rho is the soil resistivity we're looking for. Pi is just the constant, 3.14. A is the distance between the pins, which we control, and R is the resistance number in ohms that our meter spit out. You just plug in your spacing and your resistance reading, do the math, and boom, you've calculated the soil's resistivity.
So, let's recap the investigation. Our trusted tool is the digital multimeter. Our key clue is the structure to electrolyte potential. We always have to be on the lookout for our main villain, the IR drop error. Our secret weapon to defeat it is current interruption, which gives us the true instant off potential. We back up our findings with CP coupons for localized proof, and we complete the case by analyzing the soil resistivity to understand the full picture.
So, you've done it. You've followed the steps. You've got your error-free readings, your coupon data, your soil analysis. All the evidence has been collected properly. But now comes the most important part of any detective's job: interpretation. How do you take all these numbers, all these clues, and translate them into a final verdict? Is the structure safe, or is it in danger? Well, that's a question for our next investigation.